I am Giulia Pedrielli, Assistant Professor for the School of Computing, Informatics, and Decision Systems Engineering at Arizona State University. And in my research, I primarily focus on algorithms and methods for developing simulators that are able to, that enable real-time control and decision-making on large-scale dynamical systems. Today, I'm happy to share with you some aspects of my research and some thoughts on simulation-driven optimization in the era of intelligent systems in operational as well as disaster-like scenarios. I started working on the problem of optimal recovery of large-scale dynamical systems thanks to a project funded by the Center for Accelerating Operational Efficiency. There is a Center of Excellence of the Department of Homeland Security that resides at Arizona State University. That gave me a great opportunity to collaborate early on with the Department of Homeland Security and really get to understand the issues related with large-scale power networks and disasters. Among the several aspects of the project, we dealt with an issue of using real-time data at different levels of accuracy and resolution to build a large-scale digital twin for a power network that could be used in real time and be updated in real time through the data received available in several forms from power networks. So with the objective to change parameterization, but also change the topology considered in the model. This is quite important to allow dynamically and adaptively to support decision-making by several actors. In our case, we were exposed to FEMA, but there are several stakeholders that can be interested in such approaches. During our study, it became increasingly clear that we were dealing with power demand from different types of systems. And so what we started to wonder is what would be the impact of including in our simulation tools the dynamics of the system that we are serving. We started to investigate the link between power and water. So the question here was, if I consider water instead of just considering demand for power, I actually consider the dynamics of the water system and I consider the type of demand of water demand that I am serving. Will that impact the recovery policy? While this research is still ongoing, I can tell that we are finding very interesting scenarios where really we obtain completely different policies when the systems are, the water and power system are considered in isolation or considered together. So this sheds the light on the importance, I believe, to really consider this critical infrastructure as a unique network. While I haven't worked directly on traffic network design and simulation, with the collaboration with my colleagues at ASU and outside of ASU, similar reasoning applied to the transportation network, leading to really consider the need of constructing a meta simulation infrastructure that can allow us to easily integrate these tools and perform design of experiments and scenario analysis across multiple networks. A critical aspect of infrastructure such as power, water, and traffic is that they enable the functioning of critical supply chains that serve the population with food and general goods. During my study at University of Singapore, the National University of Singapore, I had the fantastic opportunity to participate in the launch of the next generation, of the Center for Next Generation Logistics that promotes the use of simulation optimization tools for the design and operation of future logistics and associated infrastructure. We have considered scenarios for food and good deliveries with advanced technologies such as unmanned vehicles, which are becoming recently much more common, especially in the pandemic scenarios. And at the current moment, we're specifically interested in analyzing what are the vulnerabilities that these new technologies subject our networks to. So in the specifics, we're interested into cyber attacks and what is their impact on next generation power, water, transportation, and supply chain configurations. Our target is always to build the next generation simulation and optimization tools that face these problems. So I'm gonna close saying that we are aware that simulators are available and have been developed for so many years in all these areas. Our interest is really in investigating how we can make these simulators better and make them digital copies of the real system when they are able to connect to the real system and change themselves dynamically and adaptively. Another fundamental aspect is, can we integrate different simulators? This seems, as I said, key in order to enable us to simulate networks of systems. And what we are also looking into is, once we have these coupled simulators, how are we going to use them to understand what are critical scenarios or aspects that we should worry about of the interconnected infrastructure, as opposed to the case where we're only analyzing a single critical system. Thank you for listening, and I look forward for the panel discussion. Thank you.
Forward share. Okay. Hello, I am Jason Iwaneski, and I'm joined by my colleague, Jonathan Clutch. We are speaking for a group that is midway through a year-long capstone project as part of the City College of New York Sustainability in the Urban Environment Master's Program. Our project's title is Integrative Sustainability Goals for a Next Generation Wastewater Resource Recovery Facility, or WRF. The work is part of an international collaboration called InSource, conducted through the Belmont Forum for International Partnership and the National Science Foundation.
Our objective is to formulate a long-term plan that shows an end state in which the treatment facility is reimagined as a campus. With programmatic elements reaching beyond the facility itself, the campus should be integrated with, rather than segregated from, its surrounding community and ecosystem. We are developing the theme through an examination of the food, water, energy nexus, as seen at 4 New York City WRFs, located adjacent to Jamaica Bay, an ecologically sensitive wetland area that is a vital stop for migrating birds along the Atlantic Flyway. Taken together, these 4 WRFs, out of a total of 14 in New York, account for nearly 20% of New York City's treatment capacity. Our campus plan addresses sustainable development goals as defined by the 3-pillar approach: environmental, social, and economic development.
Forward-thinking water recovery campuses should address sustainability's 3 pillars. In the environmental pillar, the campus should generate and store its own energy rather than be a giant load on the electric grid. Secondly, though New York City wastewater operations have evolved significantly over the past 50 years, resulting in much cleaner water surrounding the city, effluent pollution reduction remains a municipal stakeholder priority. Pillar 2, through the social justice lens, water recovery campuses should be seen as locations that endow community enhancements, such as connecting citizens with the waterfront rather than isolating as a fortress behind a barbed wire fence. They should act as an educational and employment resource for underserved surrounding communities while also protecting them from climate-related risks. And they should use recovered nutrients from waste to create a circular campus economy through food production on undeveloped adjacent lands, which leads to Pillar 3, economic goals. It's through the initiatives in Pillars 1 and 2 that we will see economic efficiencies enhanced, reducing grid-based energy consumption, more efficient effluent reuse, and a micro-circular economy built on the food and other chemical cycles. Now let's take a look at some of our proposed systems and how they align along the food, energy, water nexus. First, energy.
New York City's wastewater utility accounts for 14% of the energy usage by New York City's government public facilities, in total accounting for nearly 8.1 billion kilo-BTUs of power consumption each year. This needn't be the case. The chemical energy contained within most wastewaters is greater than the energy needed to treat it. This energy, when harnessed, can be an asset, not only for the WRF itself, but an asset to the community, providing clean, distributed energy that can provide for essential services during times of crisis. What drives this current disparity between the current state of things and what is possible? The Water Environment Research Foundation provides utilities a guide toward reaching their energy goals. Utilizing best practices across different process configurations requires 40% less energy than average for the same configurations. The rest of this energy balance can be met by getting more energy in the form of biogas from anaerobic digestion and, further, by collaboration with the municipal solid waste collection system. From data received from the utility, we were able to calculate that about 1/5 of the total load can be offset by a combined heat and power system utilizing wastewater biogas. Looking to emulate the best practices of a facility like East Bay Municipal Utility District and further food waste collection to augment this capacity, reduce transport and landfill costs, and facilitate community involvement. A WRF's core mission is ensuring that their effluent does not contaminate our waterways and beaches. In the past, natural disasters such as Hurricane Sandy in New York have impeded their ability to operate this core function. In the aftermath of Sandy, loss of grid power led to 560 million gallons of untreated wastewater to enter New York waterways. By installing distributed energy systems, resilience will be built against similar losses of grid power in the future.
The water quality of the rivers, streams, estuaries, and bays surrounding New York has, taken as a whole, improved markedly over the past several decades. Treatment plant efficiencies account for much of that improvement. The landmark Federal Clean Water Act of 1972 set up a quota system that forced plants to devote significant resources to effluent reduction plans and operations, and plant technological improvements have resulted in substantially fewer effluent emissions. But even under the Act's more stringent rules, effluents remain. Therefore, bioremediation efforts along coastlines should be strengthened, including horticultural efforts and projects like the Billion Oyster Project. The city has also allocated significant funding to changing its sewer system from a 100% combined one to one today that is 40% split. However, that remaining 60% combined system still results in 20 billion gallons of raw sewage entering waterways. These bioremediation efforts will help to alleviate these shortcomings. New York has also developed a strong green infrastructure program to combat the effects of climate change, a program that aims to improve retention through various capture initiatives, like bioswales and green roofs and underground storage. The WRF campus should be a showcase area for these technologies, featuring these innovative elements. And it will be important to monitor emerging technologies. For example, it has been shown that spent brewer's grain can assist with the biochemical oxygen demand during the treatment process, thereby helping to reduce nutrient discharge. An on-campus brewery could also offer employment opportunities and a social space. This leads to our next slide, food.
A major programmatic element we envision is to use the land directly adjacent to the WRF as an urban agricultural center. Urban gardens have been thriving in New York over the past 10 plus years, both commercially and in residences. With the onset of COVID, their popularity has exploded, as gardens can provide tangible foodstuffs in the face of broken supply chains, as well as an opportunity for people to get healthy outdoor recreation. Also, WRFs in New York City are often located in economically disadvantaged areas, neighborhoods with higher than average unemployment rates, and that have earned the nickname food deserts for their lack of healthy, fresh food options. As a result, health statistics in these neighborhoods are concerning. High levels of obesity and diabetes, for example. By providing space, resources, and education at the WRF, we see the campus as a place where local citizens can learn about and practice growing their own food. In the long term, as the gardens develop, most likely within a public-private partnership framework, we see significant employment opportunities through the program as well. At the same time, cities like New York do an awful job of making beneficial use of the potential energy found in food waste. There are many reasons behind this problem: legislative, social, and logistical issues. But the end result is a wasted opportunity for sustainability. The WRF should be a collection site for food waste in place of expensive landfills, some of which are hundreds of miles away.
The wastewater resource recovery facility can represent a microcosm of forward-thinking municipal processes sustainably integrated into multiple closed-loop systems. Treatment plants make us consider all systems along the food, water, energy nexus, and they make us come to terms with questions of environmental and social justice, and also to consider innovative economic plans like public-private partnerships. New York City's sewer system has come a long way since being developed in the mid-1800s. The original goal then was to clean up the cholera-plagued streets and to carry waste to the rivers. Evolutionary improvements since have afforded us the opportunity to change the conversation to this one, whereby we instead talk about recovery and sustainability. Envisioning future facilities leads us to the conclusion that wastewater treatment should be the linchpin operation around which to build an economic opportunity zone, like one modeled by this diagram. The campus should serve as an innovative and teaching lab for all sorts of new technologies. Some of these technologies will be in the realm of the core municipal level stakeholder directive, effluent reduction. But the deeper we dig, the more we find how that goal can touch on so many other processes, like energy and food cycle ones. Adding the integrated community layer just expands the focus and truly allows us to speak to three-pillar sustainability. All right, stop sharing. Thanks, everyone.
Due to climate change, cities are getting hotter and wetter.
At the same time, due to global urbanization, they're becoming more crowded.
Mass migration to cities makes for high density, which is efficient, although it places intense stress on existing infrastructure and affordable housing.
As cities develop the means to thrive in this 21st century, urban experts are confronting rapidly evolving challenges that break across silos of expertise.
If we are to achieve meaningful climate progress, urban experts and professionals need to leave their comfort zones and think across disciplines and across sectors. How do you decouple economic prosperity from increased climate impact? How do we grow a population without growing emissions? The district scale is the sweet spot. We can cast the net wide enough to achieve synergies between systems and economies of scale in our interventions, but also avoid the bureaucracy that can intervene at a larger scale.